All right, I think we should get started. So today we are very happy to have Andrii Neronov visiting from University of Geneva. He's going to talk about black hole micro-arcsecond scope.
Illusion is clear, right? Try to look inside with this angular resolution. Micro-arcsecond. Okay, so I'll try to tell you that we can measure something useful maybe for test of relativistic gravity using some astronomical data with, where we can get surprisingly down to angular resolution of sub-micro-arcseconds in some funny way. So the talk will be like this. I will first go through some maybe general introduction about what could we learn from active galactic nuclei from the side of astrophysics and maybe from what we would like to learn from the side of fundamental physics. Then I will switch to the main part, which will be the observations in X-rays and gamma rays. Then we will understand how this micro-arcsecond scope would work. And then last part will be that I will try to convince you that using this type of observations, we could do test of relativistic gravity with the data. Okay, so this will be around publications over the last year, these 4 papers. So, well, as usual in astronomy, when we want to do something between astronomy and fundamental physics, we are usually sort of splitting between doing some interest in astrophysics and maybe wanting to do some interest in fundamental physics. I will present something for active galactic nuclei, but the same story would work also when we look, say, for dark matter signal in whatever astronomical data only, or when we try to extract something useful for cosmology. On that, well, in the case of active galactic nuclei, on the astrophysics side, the questions which we ask, say, well, in the first place, why do galaxies have supermassive black holes, or why some of these supermassive black holes sometime go into active state, and why a subset of these supermassive black holes in active state starts suddenly to produce jets and operate particle accelerators. Well, all these questions, well, finally we want to know how the stuff works on the astronomical side. Then on the fundamental physics side, we know, well, we understand that perhaps the central engine driving these objects is a black hole. So we would like to know if the space-time around the black hole is Schwarzschild or Kerr, or do these black holes, well, really don't have hairs, or, for example, whether the cosmic censorship conjecture holds, which tells us that we are protected from unpleasant singularities which we don't understand by horizons. So we would like also to be able to use these objects to test relativistic gravity theory. Now, well, the usual story is that, well, really doing some working with the data, we don't know on which side we are. We find sort of, well, if we want to do fundamental physics, we end up with doing astrophysics or vice versa. Maybe go into some details for active galactic nuclei. This is the sort of textbook representation of how the AGN looks like. And, well, the scheme usually goes like this, well, some small fraction of AGN are radial out, operate as particle accelerators and produce large-scale jets. Some larger fraction of AGN, by some reason, does not operate particle accelerators. We don't understand why. And, well, we don't see any, well, jets and high-energy activity from these sources. Then within each population of radial out or radial quiet, there are different kinds of objects. There are brighter quasars, there are weaker, in the case of radio-loud radio galaxies, or in the case of radio-quiet, there are also brighter quasars and weaker Seyfert galaxies. Then, well, from astrophysical point of view, we try to understand why is it like this. Well, we would like to understand why is it like this. Then, if we look at the fundamental physics side of the AGN, of course, we understand that, well, if we want to test relativistic gravity, we should get close to the central engine. So for us, perhaps the large-scale jets are not interesting. And, well, the most straightforward way to understand how gravity works would be to have something like from a textbook, to have a body orbiting the black hole. And, well, say if we measure the Kepler law for the periods of the orbits as a function of distance, this would be a perfect test of Schwarzschild and Kerr metric. The only problem is that if we are talking about active galactic nuclei, the object is small. If we take a typical black hole of 10 to the 9 solar masses, put it at cosmological distance, it would span less than micro-arcsecond on the sky. So, well, we would not have, never have such a nice image of something orbiting the black hole. So, yes.
Just a naive question. So, the quiet guys, what are they active in? Why are they called AGN? So, they should be active in something. So, what do they do?
We see the central source. So,
so they don't. There is a source, but there is no jet.
Yeah, so the radio loud, they accelerate particles. So when they accelerate particles, particles produce synchrotron inverse Compton. We see something from radio to gamma ray band. And the radio quiet, they do basically nothing. Just there is matter falling into them. Matter heats typically to UV temperatures or to X-ray temperatures. I will show some detail later on. So it's just some matter falling produces, in the black hole, produces some light. Okay, so they are small, and we need to be clever to understand how to get some information, maybe like this, to get something about the orbits around the black hole without real imaging, because we would never build a telescope which is able to resolve sub-micro-arcsecond scales. Okay, so, well, first thing to do if we want to get to the central engine of the AGN, we need to understand what signal really does come from close to the black hole. Now, if I take, well, I start from taking a typical AGN. Well, this is, on occasion, this is the AGN with this name. This is radio-loud AGN. It has a spectrum which goes from radio to gamma rays, maybe spanning 10 decades in energy, and it shines everywhere, in every energy band. Part of this emission is related to the black hole, part is not very much. Then if we go step by step, trying to understand what is this, what are the components of the spectrum, the first thing which people identify with the central engine is some feature in the UV part of the spectrum called blue bump. Sometimes seen, sometimes not seen in the AGN. We think that this is coming from the accretion disk. Then next to this blue bump, there is a feature extending in the X-rays, which people well, often call hot corona. We don't know why there is this feature extending in X-rays. This feature is found everywhere in the radio quiet and in the radio loud galaxies. So this is the, well, what is common between them. Then for the radio loud, there is another part of the spectrum. Well, more or less all the rest of the spectrum is present only in the radio loud sources, and this is emission from the jet, from different distances, starting from the black hole itself, and sometimes extending to almost megaparsecs. So we understand that these two components are from accelerated particles living in the jet. This is synchrotron and inverse Compton emission from the jet. So now the most interesting part from the viewpoint of getting close to the central engine is this part which contains blue bump and hot corona, or accretion disk and well, UV and X-ray part. Typically we represent it like this. Well, now my sketch is not precise because we are not sure where we find what. Okay, accretion disk, intuitively I would put just in the equatorial plane around the black hole. This seems easy. Now when I start to talk about hot corona, which people observe in X-rays, here starts the confusion. Occasionally I I sketch this hot corona being, say, somewhere close to the wrapping out around the black hole, maybe inside the last stable orbit at which accretion disk truncates. But this is my version. Other people would plot hot corona in a different way. You will see that toward the end of the talk I will add some confusion because I will have to modify this picture somehow based on the data.
So what about, for example, VLBI observations of jets where you can actually almost see the region where they start? I mean, I think, wasn't that for one of the
M87.
M87, that's right.
So,
where
now here, now I'm talking about this accretion disk and hot corona. M87, I was going to scroll it a bit later on, but I will tell now. Say, M87 is sort of weakish radio loud AGN, so this is on this side, and this radio galaxy. Radio galaxies are some, funny objects where in M87 we are not sure that we have the accretion disk. They are intrinsically quite weak. Typical quasar is 10 to the 45 Earth per second luminosity. M87 is 10 to the 41 Earth per second.
No, but I specifically was thinking the claim that they saw the launching region that was close to the accretion disk.
Yes,
so
occasionally
what
in M87, yes, because it is so close, you can do interferometry in sub-millimeter range. There you almost have resolution to see the black hole. So I will mention this. There are two cases which we could treat like this. This is our own galactic center, which is not an AGN, and M87, which is more or less the only AGN where we would ever have a possibility to really resolve the source. I will be talking about broader class of AGN where it's just not possible by definition because they're too far away. Okay, so we have this for radio quiet, radio loud, brightish AGN. We have the disk, hot corona, where we don't know where it sits. Sometimes we also have another component. Often we have another component of emission, which is like this. This hot corona, we can see it directly, or we can see it in some indirect way, because the hot corona illuminates the disk, and the disk produces reflection and fluorescence. If there are atoms to excite in the disk, there would be also fluorescence lines. So it shines in this way. And this component of the spectrum often appears as this yellow thing over there. And the interesting thing about this yellow component of the spectrum is that in particular in X-rays we often see a bright line, which is the fluorescence line of iron. And I will stop a little bit in this fluorescence line of iron because it will play some role in what I tell later on. We see this fluorescence line of iron like this. You notice that it doesn't look like a line because it's very broad, so width of the line is comparable to the energy itself. And this is because the line is perhaps produced in the innermost part of the accretion disk. So the accretion disk rotates, and we have Doppler effect, plus if it is close to the black hole, we have also gravitational redshift. It works like this. If I take part of the accretion disk far away from the black hole, I would have a little bit of Doppler effect. So one part would be moving toward me, the other part would be moving away from me. I would have a line which is a little bit broad. But as I go closer and closer to the black hole, I would see the redshift and blue shift increasing to more or less macroscopic values. So overall, if I integrate emission from all the disk, I would have some broad line profile, which of course, now I start to feel that this might be interesting because it fills the geometry of space-time around the black hole. In principle, the profile is sensitive to, for example, rotation moment of the black hole. And here there are people who try to extract rotation moments of black holes from the shape of the iron line. Then at the same time, I understand that it is difficult to imagine that I would ever be able to get some, test of relativistic gravity. I could see effects of relativistic gravity in the line, but it's difficult to imagine that I would ever have a possibility to test relativistic gravity with this sort of data because of the nature of the signal. This is a fluorescence line, so the intensity which I detect, it depends on, for example, the way how I illuminate the disk, right? It depends also on the abundance of iron in different parts of the disk. So, if I choose a different model of this hot corona, I displace my illuminating source. Of course, I would displace the way how my iron shines, as a function of radius in the disk. And then I would change the relative normalizations of these different components of the line. So basically, if you give me some data with some line shape, I would always be able to find a model, some radial profile of the disk which would fit the line shape. So the line, the observations of the line are around for, I don't know, 20 years maybe, but people never managed to get to real,
Is there only spectral information, also polarization?
Yes, so people try to get, no, polarization, no.
No, polarization.
People try to
Is
get...
it polarized to see? It's just hard to measure polarization? Or?
It's a fluorescence emission, I don't know why would it be polarized. What people typically people try to do, they try to add some timing information. There is an obvious, easy to grab thing. If you have, I don't know for what reason, imagine that you have a single shining blob in the disk, some hot spot, right? Then this hot spot rotates, then you would see, it's small, so you would see this line from the hot spot going around like this. So if you have a big X-ray telescope, people tried to propose something like this some time ago, to have an X-ray telescope with collection area of 10 square meters. Sometimes maybe you would have enough statistics to see the line moving if the disk is flaring. Yeah, that might be a possibility.
Why is the line so asymmetric, the profile?
This is because there is a combination of Doppler and gravitational redshift. Gravitational is always redshift, and Doppler is red and blue shift. They combine in this way. Okay, so there is this line. Now maybe I will drop a little bit this radio quiet AGN, go a little bit to the radio loud where we have also jet. So we know that there is another part of the spectrum produced by the jet, like this. And the jet also originates from close to the black hole. So perhaps there is some emission coming from the vicinity of the black hole. We just need to identify what emission is this. And we put some limited possibility to do this if we study variability of emission. Well, typically something big would be variable on long time scale, something small would be variable on short time scales. So if we take a 10 to the 9 solar mass black hole, our reference variability time scale would be around 1 hour. This is light crossing time of horizon of a black hole. Then, if we do this argument, we understand that it is the gamma ray and X-ray emission, so the highest part of the synchrotron and the highest part of the inverse Compton spectrum, which might come from close to the black hole. And this is how it looks like. This, if we plot the resolution is not good here. This is variability time scale as a function of estimates of black hole masses for the sources which are observed in gamma rays here by Fermi telescope. The lines here is the light crossing time of horizon for Kerr black hole, maximally rotating. This is the light crossing time for Schwarzschild black hole. This is the last stable orbit period for maximal Kerr. This is the last stable orbit period for Schwarzschild. So we see that, there are some sources which really touch the variability time scale, which is the light crossing time of horizon. And, you can check that the sources which are in this part, this blob here, they don't touch this by simple reason that this Fermi telescope, it has limited sensitivity, so the statistics of the signal, these are weaker sources than those ones, so the statistics of the signal here is not sufficient to see variability on very short time scales.
What is this y-axis?
Y-axis is the variability time scale.
Variability time scale defined how?
Well, if you just take, so typically the sources are flaring, and you can define, if you see isolated flares, you can define, say, flux doubling time. Or you make a power spectrum, then you see that it has power up to some frequencies. So if you do...
Which is these?
Hmm?
These are flaring sources, or these are from power spectra, or what?
What was it? I guess it's the analog of power spectrum. It was called structure function analysis.
Right. Yeah. That's what they call it.
Yeah. So,
I mean, I'm just wondering how much like this y-axis is tunable depending on exactly how you cut off.
yeah.
But I guess these are orders of magnitude on the y-axis now. That
Yeah. So, if you consider it as an order of magnitude, then it's robust, right?
Yeah.
But then, of course, you need
factors of 100 there.
to define what is your what do you choose as variability time scale.
So does it include any QPO planes, so the quasi-periodic oscillations that some people...
Surprisingly, there are not so many QPOs in gamma rays. That's well, naturally, if this is something related, say, well, if the jet is launched somehow by the disk, which is unstable, you would typically expect some QPOs, but there are no results like this. These are not QPOs. There are cases when people see, sometimes we think that there is a binary black hole there. These are easier to spot periodicity patterns, but not QPOs on these time scales. So this, we have some data from Fermi. Then also Fermi is, it's small telescope in the sense that its collection area is 1 square meter flying in space. We can get much better statistics of the signal if we use ground-based telescopes. So people doing ground-based observations, they also spotted that some of the sources which they observe are variable on the really black hole light crossing time scale. Okay, so now when we understand that perhaps this gamma ray signal might come from close to the black hole, if we look from the astrophysical side, this would already give us some useful information on how this, this should come from the base of the jet, how this jet is produced. There are different competing models. We don't have clear understanding. Say I scroll through one model like this. It's based on Blandford's-Naik process. It tells us something like this, that the black hole is surrounded by a magnetosphere where rotation of the black hole generates point in flux, which is going in direction, so in preferred direction this would be a jet. But in this model there is some inbuilt gamma ray emission, because the black hole typically, the black hole magnetosphere, so would have some defects or gaps in the magnetosphere where there is an electric field accelerating particles. So typically if we do some calculations, this electric field, particles accelerated in electric field going through magnetic field would produce synchrotron or curvature emission and inverse Compton emission in the gamma ray band. And then in a second step, of course, we are living in some dense environment. The accelerated particles and the gamma rays, they would initiate particle cascade close to the black hole, and this would lead to some secondary component of the spectrum, which would be synchrotron and inverse Compton. So in this sense, if we try to understand these variability patterns of gamma ray signal, we might sort of confirm or disprove this possible mechanism of jet production. Now, well, we can understand something about astrophysics, but it's again difficult to imagine that we would extract something useful from this data from the viewpoint of testing gravity. Again, in the case of Blandford's-Knight mechanism, we are observing some general relativistic effects because this rotation of the black hole drags magnetic field, and this produces a point in flux after all. But well, not possible to extract something, something which is which is free of unmeasured functions. Yeah. So now to add more complication, this so my sketch for the radio quiet, radio loud. There are also different variations of this scenario. Say this M87, which you was mentioning, would be not like this and not like this. There is perhaps no accretion disk. Instead, there is radiatively inefficient accretion flow, which is sort of like hot corona, but still more hot than the corona in bright quasars. So then, well, difficult to build some well understood model for this. Now, of course, it would be better to go and observe, to really resolve the sources to see some details of these three schemes there. Now, if we take the angular scale like this, it's only in the case of M87 when we would be able to resolve the source in the future, because this is a large black hole, like 7×9 solar masses, at very small distance. So if we plug in these numbers here, it will give us something like 10 micro-arcseconds. And this is the resolution which people could in principle get to with very long baseline interferometry. But beyond M87, we will never see any resolved picture like this.
What is the scale of that picture? The physical scale?
No, that is a very large scale image. This is
like megaparsecs?
I think 100 kiloparsec. Okay, so now I will still try to convince you that we can resolve something on micro-arcsecond scales, and I will use devices like this for these micro-arcsecond observations. This will be just gamma ray telescopes. Well, there is Fermi telescope. This is pictured here. Since December last year, we have some, not competitor, but something parallel to Fermi. This is a Chinese device called DAMPE. And these devices work as pair conversion telescopes. So gamma ray comes in the detector, produces electron-positron pair, and people track the trajectory of the pair. With this, they get to the angular resolution, which is around, well, at best 0.1 degree. Never reaches micro-arcsecond by far, yeah? And looking at how the technology works, it's difficult to imagine that some clever trick would improve you by something by 6 or 7 orders of magnitude. Otherwise, the other telescope which I will mention is, let's say, MAGIC telescope pictured here. This is a ground-based gamma ray telescope. Works more or less on the same principle, but in this case, the conversion of photon into pair takes place in the atmosphere, and the electron and positron initiate a cascade in the atmosphere. And these telescopes, these are UV telescopes sampling Cherenkov light from particles in the shower in the atmosphere. Again, with this technique, people get 0.1 degree resolution comparable to Fermi, but would never be much dramatically better. We can do a little bit better in X-rays. I will also discuss some X-ray data. Say the best example will be Chandra telescope, which has angular resolution around 1 arcsecond. And the worst example in my following presentation will be Swift telescope, which has angular resolution around 10 arcminutes. Well, if we think whether anything could be improved in these technologies, we see that all the next generation developments, like for space-based gamma ray there is a next Chinese project called HERD for ground-based gamma ray. There is a European project, European, US, Japan project called CTA. And for the X-rays, there is a next generation project, Athena, of European Space Agency. They all go in a different direction. They don't try to improve angular resolution. Some of them will have worse angular resolution, but people just try to get more collection power, so larger effective areas. HERD is larger than Fermi and Dampe, CTA is larger than MAGIC has in Veritas, and Athena has mirror, which is larger than XMM and all the others. Nobody tries to improve angular resolution. Okay, so then we need to get to micro-arcsecond scales, we need to get something else. So my proposition to use will be to use some addition to the telescope, which will be the gravitational lens. So I supplement this optical system with more powerful optical system. And let's see how it works. I take, I will be discussing this particular source, so this is a radio loud quasar. I will be using the data of Fermi telescope, so nominal angular resolution is like this, 0.1 degree. And I will take a source which is a known strongly lensed quasar this is the radio band image. It is resolved in the radio with angular separation 1 degree, 1 arcsecond. So already this is not resolvable by Fermi. But so just to scroll through the data, this is the spectrum of this quasar. I see, in this picture I see the inverse Compton bump, so from X-rays to gamma rays. And then, as I told before, the gamma rays are very variable. This is the gamma ray light curve. The X-rays are more stable, so this tells me that perhaps gamma ray emission is more compact than the X-ray emission. Now, that's more or less all I can get from gamma rays and X-rays. I can get spectrum and light curve. Imaging is not very informative there. I just see the source. Now, when I look in the light curve of the source, I see some interesting structure. I see that, this is the same gamma ray light curve as in the previous transparency, more or less expanded into more details. So I see that the source produces flares. For example, this is a pronounced flare. But then it produces again another flare like this. And the process is always, the flares always appear in time, in pairs. If I do a structure function of this light curve, I see that there is a feature in this structure function at some time delay, 21 days. This is more or less the distance between the subsequent flares. I know that this is an interesting time scale because this is close to the time delay between gravitational time delay between the two images of the quasar. It was reported more or less at this in this range in radio some time ago, but the radio paper gave some confusing, self-contradictory measurements. So redoing the radio analysis, I see that I get some best fit somewhere at 21 days exactly as I see in the gamma ray band. And I know how to interpret this time delay. In both cases, I see the gravitational time delay between the two images. So, in a sense, I could not resolve the source with normal imaging, but I resolve the two images in the time domain. I will try to reuse this principle throughout the talk to push it a little bit further.
Just to make sure I understand things, so what you're saying is this time delay is just received from the front side, basically, that arrives at some point, and then we see the 21 days later that is due to the back side, basically, of the flaring event, and that had to cross. Now, this
is the difference of the light path between the two images, say. If I have my source over there, I have the lensing galaxy somewhere here, I'm observing here, here, yeah? So the light which goes like this, it takes a bit longer or a bit shorter than the light going like this, yeah? So my at these images of the source. So my one signal in one image would be delayed compared to the signal in the other image, right?
Yeah, I mean, the past can't be the same, otherwise there should be a right
Yeah,
at the
yeah,
same
should
time.
be,
So it's just
should
slightly
be a little
different
bit like
patterns,
this.
right?
Yeah. Okay, so now.
But then it tells you more about the source. I mean, it tells you more about the lensing source, right? So I'm not sure how you still get, because the gravitational time delay is due to the source itself that is lensing it. So I'm not sure what you learn about the part portion. Or is that going
It's due to lensing. The gravitational time delay is due to the lensing.
Exactly. But
It doesn't. At the moment, it does not tell me anything about the source, right?
Okay.
It's just it's a curiosity that I have a source which is a couple separated by one arcsecond, yeah. And I know that it's separated by 1 arcsecond because I resolved the source individual flares from the two components, right? So now I will try to convince you that I see something even more about the source in this data. The story goes like this. I know that gravitational lensing is a chromatic phenomenon. So my time delay in radio is the same as the time delay in gamma rays. Obviously, I'm just tracing light rays. The same should be true also for the relative brightness of the two sources. In radio, I see that one source is more or less by a factor of 1.5. This is flux magnification ratio, the quantity like this. So it tells me that one component is by a factor of 1.5 brighter than the other component. Normally, I would expect that in this plot, if I have one flare, the second flare should be 1.5 factor of 1.5 higher or lower, depending on who comes first, right? Always, in every flare. If you look, even not zooming on the light curve, you see that it's not like this. First of all, already looking at this flare, I see that it's not a factor of 1.5 between the two flares. Then, looking at the subsequent flares, I see that, well, in fact, the relative normalization of the two flares changes in time. This is, well, something interesting, yeah? Let's say like this. I'm a bit lucky here. I have this strange, I don't know what explains some repetition of the flares. If I have one flare, I always have the flares after some 75 days. Well, it helps me in what I will tell on the next transparency. I know that my flux magnification ratio changes on the time scale less than 76 days. I use it operation, yeah, but not questioning, not asking what is the other time scale. So the explanation for this would be like this. This is called the effect of microlensing. If I just consider a lens, let's say elliptical lens, a source behind an elliptical lens, I know that the number of images, the relative brightness of images of the source depends on the position of the source with respect to the lens. Say, for this elliptical lens, if I put the source exactly behind the lens, I would see 4 images. If I move a source a little bit away from the lens, I would see the 4 images going somehow to the right and to the left. And at some point, 3 of the 4 images would collapse when the source position crosses some line in the source plane called caustic. So then the 3 images would annihilate and into one image, and then moving still further away, crossing another caustic line, I will be left with only one image. And the brightness of these images changes depending on my relative position to the caustic. So this works for the whole galaxy as a lens. It also works if I have a star in the galaxy, which is occasionally aligned along the line of sight. I will have the same effect. If I put the star exactly in front of the source, well, I would have this caustic pattern, well, more or less in front of the source. I would have this caustic pattern for the star, and depending on how my source is situated with respect to caustic, my signal from the source would be, well, the number of small images, well, of the source. The source would split onto many small images, and the total brightness of these small images depends on how the source is situated with respect to caustic. I could take one star, I could take the neighboring star, it would have its own caustic, and the source would be situated differently with respect to the caustic of the other star. And I could take all the stars in the galaxy, well, the caustic pattern of the stars would look like this. So now I understand that if I change the position of the source with respect to the caustic, where is it? Yeah, like this. If I move the source with respect to the caustic, my appearance of the source would be different, and then the total brightness of these different images of the source, let me scroll again, would also change. The source would be brightest if it crosses, well, the overall flux from these images would be brightest each time when the source crosses the caustic. This map which I show here, it's actually the color scale here is the total magnification of the flux due to gravitational lensing. So now, of course, if I'm looking at the macrolensing, the entire galaxy and the source behind it, my source does not move with respect to entire galaxy, almost does not move. But if I take stars in the galaxy, I know that all stars are moving. And in fact, our position in the Milky Way changes with time, so we are all moving with 200 kilometers per second. We have stars in the lensing galaxy also moving 200 kilometers per second. And the host galaxy of the source is also moving somehow. So, in fact, this movie which I've shown you, it's a real, well, should be a real effect. So, this caustic pattern moves, and my microlensing effect is expected. Well, this effect of lensing by stars is called microlensing, and it is expected to be variable in time. And I just observed this effect in the gamma ray data. So now, well, this is useful. I could extract something useful from this observation of microlensing. Well, just a couple of formulas like this. My overall magnification of the source behind the caustic, it is larger for a source of smaller size. More or less, well, the exercise which I would do to calculate the maximum magnification. If my source is like this, I would integrate the magnification factor of a caustic map, and then when I cross the caustic, I would say for smaller source, I would integrate more reddish part than for larger source. So overall, this scales as inverse of the square root of the source size. And then the time scale on which my magnification factor changes, it also depends on the source size. Well, it's basically given by the transit time of the source behind the caustic. It more or less, it would the magnification would change on the time scale of 100 days if my source is this small for the parameters of this source which I'm discussing. So just from the mere fact that I have observed the change of the magnification factor on 76 days, I derive that my source is compact. I've also observed some particular magnification factor, and I have a second estimate of my source flux. It could be around well, an order of magnitude increase in the source flux if the source is this small. So, well, imagine I don't have at all possibility to resolve 10 to the 14, so 10 astronomical unit scale at cosmological distance. But in a sense, I resolve this in the time domain again. I have some information about the source size. There is even more interesting thing. I have multi-wavelength data. I have gamma ray light curve. I have X-ray light curve. So this is hard X-ray light curve. And I see that, well, all these flares, I know that they are strongly influenced by caustic crossings, by this microlensing effect. I don't see the counterpart of these events in X-ray light curve. This means that somehow my X-ray source should be larger than the gamma ray source, and here is the model for this. If I follow, so this is well, the same simulation, but for X-ray source I took a larger size, so it convolves, the caustic map convolves with larger kernel, so the variability pattern is smaller. So what I see from this data, I see that my source size is dependent on the energy. Different parts of the spectrum come from different distances. That's what I conjectured based on variability properties before. But now I have direct demonstration of this. I know that my GeV gamma ray source is compact, more or less 10 astronomical units. It's the base of the jet. My black hole is more or less this size. And my X-ray source is large, should be larger than some characteristic scale called Einstein radius of the microlens. So should be in the range of 10 to the 17 centimeters. A nice exercise. I didn't expect this with telescopes which are 1 degree angular resolution. I get some information about structure of the source on these distance scales. Now, just maybe scrolling quickly through another source which is similar. We did Fermi analysis for this source and we also see caustic crossing events. This is the variability pattern is more complicated, and we even see evolution of this magnification flux magnification ratio in time. This source is interesting because it is also observed by the ground-based gamma ray telescope, this MAGIC telescope. Occasionally it has detected the source. Not thinking about this microlensing stuff, but there was a Fermi, reported Fermi flare of the source. They pointed to the source, they see another flare. They detect the source some time after the flare, and there is a lucky coincidence that they have measured the gravitational time delay like this, because they pointed the telescope at the right moment of time. The gravitational time delay in this source is known to be around 10 days, so they saw the second component, the flare from the second component, which Fermi was even not able to detect because it doesn't have enough sensitivity. And this is the spectrum of the source over there. So one needs to, well, there is a potential for study of microlensing with ground-based gamma ray telescopes. They observe at a little bit higher energies. Fermi is giga electron volt, and ground-based telescopes, they are 100 giga electron volt or tera electron volt. So combining the data, we potentially might see, well, this energy-dependent source size.
So when I've seen this done in the past with optical and IR and radio data, for in this case constrained, I think the sizes of like the broadline region, things like that. The limitations come in from things like dust in the lens and things like that, which can which also affect the relative flux ratios. And I'm just wondering, like, can you compare like how doing this at these high energies compares to that other?
Well, there is no dust affecting the flux in gamma rays. This is,
I would presume that it would be very unusual to run into the right enough dust in the disk of a galaxy. Yeah, but I'm just wondering, like, are there other propagation effects that matter, or
not
no?
much, yeah. If we go to very high energies, to TeV band, this source is not observed in TeV band because the flux is, well, you see the cutoff here, but the cutoff is because the gamma rays could not get through the intergalactic medium. Well, they interact with low energy photons.
Yeah.
Well, this is the obscuration, but well, we don't go to this energy band yet.
Right.
Maybe we will, I don't know. Okay, so we could do something with MAGIC. We could do a much better job maybe studying microlensing in more details with much higher statistics with the next generation telescope. Well, the advantage of these ground-based telescopes is that, say, this device will reach collection area of 1 square kilometer compared to 1 square meter of Fermi. So well, basically the error bars will be non-existent in this signal. So then maybe go into, well, this was about radio loud. I sort of learned something about that gamma ray emission comes, GeV gamma ray emission comes from the base of the jet. I will temporarily switch to the radio quiet site. I will consider another source, which is a radio quiet quasar. This will bring me to this test of relativistic gravity in some short time. The source is like this. I will be using Chandra and Swift telescopes. Chandra is much better than gamma ray telescopes. It has an angular resolution of 1 arcsecond, and I see that this source, well, this is some quasar with these parameters. The images has 4 components, and they are resolved by Chandra. They are not resolved by Swift but telescope, and moreover, for some long time, Swift was not able to detect the source, but suddenly, after 2009 or so, it started to detect the source. And, well, if I look at the spectrum of the source, I see that it's quite boring. This is typical for these radio-quiet sources. In X-rays, I see emission from the hot corona. I see a little bit of, well, what is called soft excess. Nobody knows what is this. There are debates of what kind of signal is this. And, well, in this particular source, I also see broad iron line. It appears like this, like wiggles in the spectrum. And then, if I take the light curve of the source with Chandra, well, these are optical data where all the components of the source are resolved. And, well, here I plot the flux of the components, but also the ratio of the flux. I know that the time delay between these components is small, so I could spot microlensing right away if I just plot the ratio between the fluxes. I see that this ratio varies in time. If I take Chandra data, I see that it also varies in time. And I understand that at some point in X-rays and in optical, the source went behind this microlensing caustic. This was caustic crossing event. And, well, at this moment of time, Bud started to see the source. So perhaps, well, we were helped by this flux magnification by microlensing. Again, if I do some analysis, I see that the microlensing time scale changes with energy. I know that it's 60 days at 3 keV and 600 days at 30 keV. So I know now that my source has energy-dependent size. And if I look at my sketch, which I put before, I need both components of this picture. I need the compact hot corona at 3 keV and the larger hot corona at 30 keV. Again, I'm starting to, with this method, I'm starting to learn how the stuff works in the direct vicinity of the black hole. Now, we'll not go through explanations of this, but possibly.
Should I be surprised that the hotter gas is?
Yeah, that's I told that I don't want to go to the explanations.
Okay. All right.
Yeah, let's leave it for discussion.
Okay.
Yeah. I want to go to the iron line, so I come back to this image which I've shown before. Now I add microlensing there. It would work like this. I put a caustic. This will be my line representing caustic, moving across the source. How it will affect my iron line? It will do something like this. I approach from the red side, and I would well, amplify or magnify the flux of the source, which is just behind the caustic. So it will magnify this part of the disk, which is moderately redshifted here. Moving further into the source, I would magnify a bit more redshifted part, and a bit more redshifted part, and still more redshifted part. I am reaching the last stable orbit and moving to the blue part. So suddenly I start to magnify the blue part of the line. And then I move away, and then my magnification dies. Overall, it would produce a picture like this. Now, in this picture, it's a time sequence of spectra. This time goes in this direction, and every vertical line of pixels is a spectrum. Now, we see that, well, this is, now, the exercise done in this simulation is like this. I take some accretion disk. It's an image of accretion disk, typically with strong, well, with lens, and it's deformed. I put it behind this particular caustic. It's a simulated caustic representative for the source of my choice. And I run the disk behind the caustic and calculate how does the spectrum of the line change. And I see this effect which I sketched qualitatively, that my sort of line, amplified part of the line shifts in time. It draws me something like this curve. In a sense, this curve is a velocity curve. Also, it's a rotation curve of the black hole. It depends on the parameters of the black hole. Well, it depends on the number of parameters. Say, if I take a black hole which is non-rotating, black hole which is rotating, this evolution of the line is different because the velocity pattern is different. Of course, the overall evolution of this most magnified part of the line depends on the inclination of the disk. This is different inclinations of the disk. Depends on a couple of more parameters, but no free function there. It's just finite number of parameters. Remember when I was discussing the shape of the line, it depends on everything it likes, on the way how we put the illumination around the disk and so on. This is just a trace of the edge, well, the most magnified part of the line. So the shape of the line would change depending on what model do I choose or what is the real situation, but the edge is always the same. It's just the red shift or blue shift on the line of nodes of the disk. So the middle line where I have most of Doppler effect. Okay, so that's how it works. I could measure something from what some useful stuff about the black hole. Say I see that in particular for the disk which I see face on, this curve has a plateau. This is just when I am passing in front of the last stable orbit. It has the plateau has depths which is different for rotating and non-rotating black hole. This is because the redshift for rotating at the last stable orbit for gravitational redshift at the last stable orbit for rotating and non-rotating black hole, they are different. And it has also a descending and ascending part, the shape. This is really the rotation curve as we see in galaxies or in solar systems. So this is the Kepler law, but in general relativity, which I am observing here, or potentially could measure. If I go to these questions which I asked at the beginning, I know what parts of this curve correspond to what questions in my initial part of the talk. Say, if I would imagine that this is a black hole with a hair, it would, the hair would distort the rotation curve here. It would, say, shrink or expand the last stable orbit and so on. So there are things to measure about gravitational field in this data. Now we are trying to catch, to measure this rotation curve of the black hole using a combination of different data. So for the beginning, we need to catch this caustic crossing event somehow. They are rare. If you look at the time scale here, this is 1,000 days, so we really should not miss one, right? It happens more or less once every 3 years or so. So if we monitor the source in optical and also in X-rays to see if there are variations, some sudden flares, we might catch these events, and then when we are at the coast, we are sure that we are at the caustic crossing, we ask an observation with, this is the most powerful X-ray telescope with the largest collection area, to get more or less the best signal to noise for this picture, right? So that's the idea. We are waiting for the next caustic crossing events, like this. We can also do a little bit with Chandra, but Chandra is smallish, but still useful. The effect which I am discussing was occasionally already observed with Chandra. People saw in some previous observation that the iron line has moved between different observations. And in fact, they claim that it has an even split. This would be possible when I'm just at the last stable orbit, so I have a part which is red-shifted and blue-shifted simultaneously. Now, this would be some test of gravity if I would measure this rotation curve, so some test of general relativity. We can ask whether it has much sense when we have this new gravitational wave data where apparently general relativity is confirmed in all its glory. There are differences, some useful things which we can look at. First of all, these are different black holes which we are discussing. These black holes seen by LIGO are produced in stellar collapse. So their formation history is different. We actually don't know where the supermassive black holes come from, right? So maybe they inherently, captured some interesting fields and they have some hairs which stellar mass black hole would not have. Otherwise, there we are dealing with highly non-stationary situation. This is nice and well, stable situation in the, so it's a clean Schwarzschild method.
Just out of curiosity, what you said implies that the fit that the LIGO did, they also did try to fit with some unusual black holes with here and stuff.
Yes, that's the next point. Well, it's difficult because you need to run some numerical simulations, and well, already in general relativity it takes them a lot of efforts. Maybe in future, well, we don't know. The computing facilities are evolving very fast, but to test a reasonable range of models with LIGO data is challenging, right? Here I just do calculations. I take a textbook and I redo the calculations, or well, it's almost analytic. And then also it's a different sort of test. Here I'm really scanning through the space-time. I'm measuring metric as a function of distance. There I'm more sensitive to some sort of integral characteristics. I don't know, this ring down is some overall characteristic of the black hole. So then the precision, I'm not sure who is more competitive. Would they be more precise than this test or not? This is to be assessed when we have the data for the transit of the caustic. Okay, so maybe general relativity is confirmed, but it's better to measure still. I'm not sure if Zwicky meant to discover dark matter when he was studying the dynamics of galaxies in coma cluster. Perhaps he wanted to make a simple check that coma cluster is kept together by gravity, right? So even if we are sure that general relativity is good, let's measure if we can measure this. More or less, that's what I want. That's the message which I wanted to bring to you. And I'm at my conclusions. Oops. Yeah, well, that's all.
Questions?
So coming back to this, the last point about checking GR.
Yeah.
I mean, what are the prospects? I mean, how accurate you can be?
That's what I meant when I told that let's get the data. So,
Yeah, I mean,
in principle, infinitely accurate. If I, well, if
I mean, you
say,
can only infinitely accurate on finite time scale. So on a
well,
finite,
infinitely in an operational sense. But let's say this caustic transit for the source which I was discussing, it lasts for 3 months. If I order an observation with XMM telescope, well, once I have this, well, this is a target of opportunity. Once I have a hint of caustic crossing, go to the source and stay there for 3 months, or better, half a year. Then the signal to noise would be good. I would be, well, then what I would do with the data, I would try to, well, get rid of the garbage, which is shape of the line. I will try to trace only this evolution of this edge or sharp feature, yeah? Then, of course, there, it depends on the signal to noise which I have. So if I have a deep exposure with XMM, I could get to some reasonable precision, more or less, to this picture, right? For the moment, the target of opportunity which we are awarded is, say, 5 observations of some limited exposure over the caustic crossing to make to demonstrate that it works. So the first task would be to really put some points here. Well, then,
I mean, so what's the, in other words, I'm just saying, let's be optimistic.
mm-hmm.
So if I would say, let's say, I don't know, you want to check gravitational hair or whatever, no hair theorem or whatever. So let's say, what could be the accuracy? So let's say, presumably there is this hair, it affects the
before this, the more simple task would be to see if this is consistent with, say, Kerr or Schwarzschild, right? Here, I see that the difference is sort of, it's macroscopic, right? The displacement of the line is, say, well,
so what would be the accuracy,
energy.
like delta G over G? Let's say I'm a particle physicist, I want to know if,
Yeah,
what it would be like. What's the optimistic case? 1%,
No, this I didn't try to estimate. I want to get the effect detected at the moment. I didn't try to estimate, well, what will be the precision of. Well, first of all, I need to define in what units I want this precision.
Dimensional
Right?
units, delta G over G. I mean, there is a metric, right? Let's say Einsteinian metric.
Yeah.
And if there is some change into no hair theorem or whatever, presumably there will be some deviation from what you expect. Let me call it like delta over delta G, some relative change of something. Now my question is, I mean, in the maximally optimistic case, I mean, what can we expect? I mean, how accurate? Because we understand that if there is this sort of
So the most
understands-
optimistic case for existing telescope is like this. I have, say, a natural limit, which is energy resolution, right? Whatever is my statistics, I would never beat the energy resolution of the instrument. The energy resolution of XMM is 10%. So I could do in the infinite statistic, well, not infinite, but in the reasonable statistic case, I could do delta G over G 10%.
10% is the most optimal.
Yeah.
Is the optimal thing.
Then, well, there
That's
is.
a little bit, that's a little bit pessimistic because, I mean, we understand that, you see, if there are corrections to these no-hair theorems, they must be extremely small. It cannot be that
Well,
no-hair
no,
theorems
it's,
are simply wrong.
it's on different scale, right? You know that
Yeah,
they're
it would be
extremely
scale.
small on binary pulsar scale or something, yeah?
Well, I mean, higher is the scale, typically they are even more negligible, but okay, I mean, I'm just saying, so this would be good to have, so 10% is huge. 10% change to,
You ought to be able to centroid that line into a lot better than 10% if you had infinite.
Yeah,
you
that's
could
what
do-
I meant. In the
so you-
infinite statistics, I would be also able
It'd be
to
one-
center the line
Right,
better.
but it's also pretty reasonable to say you can get 10 times your resolution if you're centering a line, right? So,
yeah, well, I'm not with.
but 1% might still be huge. I don't know.
No, of course, if there is
Yeah,
something,
then
something
there's
positive.
just say 2 weeks ago there was a telescope launched which has a high resolution X-ray spectrometer. It's not with this telescope which we would get better than 10%. Formally the resolution there is several hundred delta E over E, but the effective area is very small, so you need very bright source. There will be still next telescope based on the same principle, more or less with the same spectrometer called Athena. It will have large effective area and high spectral resolution, so well, things would improve. But I didn't try to estimate in your terms because at the moment I'm just trying to get the effect detected really like this. So.
No, I understand, I'm not criticizing, it's just,
So
I'm asking as a user.
in your terminology, electromagnetic field is here or is not here?
You mean
Let's say-
charge?
Yeah.
Well, that's not exactly what we expect from an astrophysical black hole, which
No,
should be
but
largely neutral,
that's
right?
why, yeah, well, you don't know, the probably that's what
Yeah, I
you
don't
check.
know. Maybe, or maybe this is a charge of some other field which I don't know yet, right?
Could be, but on your graph it will reflect in similar type.
Yeah, it will move the curve more or less. Well, if we take Reisner-Nordström, it should be well the same. Or the order of difference between the curves would be the same as between just Schwarzschild and Kerr, right?
Right. That's another test, I suppose.
To see if it's really
Yeah.
neutron.
Yeah.
But charge has to be huge, right?
Yeah.
Yeah, it's. should be
10% of its
huge.
mass.
But then, I mean, you will screen it.
Probably.
By-
Yes,
by
that's
reference,
what
you
I
know,
will-
But you are probably very nearby, right?
Really fascinating.
Yeah.
No, typically we don't expect
I know.
any charge. Yeah.
I'm trying to find out ways to test.
And this requires having a lensed quasar, a lensed AGN with a bright enough K alpha line.
Yes,
And is this like the one?
there are
No?
several.
There are
Yeah,
several
not
like
so
that
many.
that are lensed? Because I thought this K alpha profile was only measured in like a handful of sources at all. But you're saying that more than one of them is also lens.
Yes, so I know at least two. That's
Okay.
for which I'm submitting the proposal.
Right.
But maybe you will find more.
Well, not me.
Well, Well, there are surveys, maybe there are something which we have overlooked somewhere, right? Maybe, well, go into different new gravitational lenses with X-rays, we will find more of those lens with iron lines.
Any other questions? Okay, thank you, Andrii.